For centuries, our understanding of gravity has been shaped by the groundbreaking work of Isaac Newton and later, Albert Einstein. Newton's law of universal gravitation provided a mathematical framework to describe the attraction between objects with mass. Einstein's theory of general relativity revolutionized our understanding further. It proposed that gravity is not a force but a curvature in the fabric of spacetime caused by mass and energy. However, a new hypothesis challenges these established notions. This hypothesis suggests that gravity is not a fundamental force, nor is it solely a consequence of spacetime curvature. Instead, it proposes that gravity emerges from the disruption of intermolecular bonds at a quantum level. This disruption, the theory posits, generates a thermodynamic gradient that we perceive as gravity. Imagine the universe as a vast network of interconnected molecules. These molecules are constantly interacting and exchanging energy. When mass is present, it disrupts this delicate balance. The disruption creates a kind of pressure toward the mass, pulling other objects toward it. This new perspective offers a radical departure from conventional theories. It seeks to explain gravity as an emergent property of thermodynamics, a consequence of the behavior of matter and energy at the smallest scales. This new hypothesis, while radical, attempts to explain observed gravitational phenomena. One of the most intriguing aspects of gravity is its effect on light. General relativity explains the bending of light around massive objects as a consequence of spacetime curvature. Light, following the shortest path through spacetime, appears to bend as it travels through the warped region near a massive object. The new hypothesis offers a different explanation. It suggests that the disruption of intermolecular bonds by mass affects not only matter but also the very fabric of spacetime. This disruption, according to the hypothesis, alters the path of light, causing it to bend around massive objects. Another key gravitational phenomenon is redshift. Redshift refers to the stretching of light waves as they travel through expanding space. General relativity explains redshift as a stretching of spacetime itself. As the universe expands, the fabric of spacetime stretches, causing light waves to stretch as well. The new hypothesis, in contrast, proposes that the expansion of the universe is driven by the cumulative effect of intermolecular bond disruptions. This expansion, according to the hypothesis, affects the properties of spacetime, leading to the stretching of light waves and the observed redshift. The differences between the new hypothesis and general relativity extend to the explanation of tidal forces. Tides, as we know them, are caused by the difference in gravitational pull from the Moon across the Earth's diameter. General relativity explains this by highlighting the varying curvature of spacetime caused by the Moon's presence. The new hypothesis offers a contrasting view. It proposes that the varying density of intermolecular bonds across the Earth's diameter, influenced by the Moon's presence, creates a difference in the pressure exerted by the disrupted bonds. This difference in pressure, according to the hypothesis, manifests as the tidal bulges we observe. These contrasting explanations highlight the fundamental difference in how the new hypothesis and general relativity approach gravity. General relativity views gravity as a geometric property of spacetime, while the new hypothesis sees it as an emergent property of thermodynamics, arising from the interactions of matter and energy at the quantum level. Perhaps the most tantalizing aspect of this new hypothesis is its potential implications for some of the most profound mysteries in cosmology: dark matter and dark energy. These enigmatic entities, while invisible to us, are thought to make up the vast majority of the universe's mass and energy. The new hypothesis suggests that the observed effects attributed to dark matter and dark energy might arise from our incomplete understanding of gravity at the quantum level. The disruption of intermolecular bonds, according to the hypothesis, could create additional pressure that mimics the gravitational effects currently attributed to dark matter. Furthermore, the hypothesis proposes that the cumulative effect of these disruptions on a cosmic scale could be driving the accelerated expansion of the universe, an effect currently attributed to dark energy. If proven true, this new perspective could revolutionize our understanding of the universe's composition and evolution. It offers the tantalizing possibility of unifying gravity with the other fundamental forces of nature, a feat that has eluded physicists for decades. It is important to note that this new hypothesis is still in its early stages of development. It faces significant challenges, including the need for rigorous mathematical formulation and empirical verification. However, the potential of this hypothesis to reshape our understanding of gravity and the universe is undeniable. Only through continued exploration and rigorous scientific inquiry can we determine if this new perspective holds the key to unlocking the universe's deepest secrets.